Okay, thank you. So today I wanted to talk about this four-dimensional Chern-Simons theory and its relation to the two-dimensional integrable field theories and how to construct this landscape of integrable field theories. I heard about this approach from the Sylvain Lacroix's lectures on this summer school, integrability and duality. And I thought it's like really brilliant idea. And, you know, it's like almost effortless method to construct all those integrable field theories. And so here's this review paper and the Sylvain's review paper. It's basically the lectures encapsulated in this paper. Oh, by the way, when I move my mouse, do you see it or?
Yeah, we can see that.
Okay, so and this approach was first introduced by Costello, Yamazaki in this paper. So it's quite new. And actually these papers are, I think, some series of papers, and this paper is actually the third paper on this series. In the previous ones, they introduced this from the four-dimensional Chern-Simons theory, they obtained this lattice theories. So in this actual paper, they obtained they introduced how to obtain this four-dimensional integrable field theories. So this is, I think, the original paper. So so I basically don't know anything about integrability, so I just try not to say too much about this integrability. So, but let's just start. Just a simple reminder that when you study two-dimensional integrable field theories, to check if the theory is integrable, then you need to construct this Lacroix matrices connections, and let's say so you need to construct these Lax pairs, and this Lax pair needs to fulfill this. Actually, the zero curvature of this Lax pairs should be the equation of motion of this given field theory. So if this Lax connection is fulfilled, then it's the starting point for this integrability, I think. So, but the important point here is that this Lax pair has to depend on the spectral parameter Z, zeta. And then these smart people thought that, okay, so this reminds us something. If you look at the three-dimensional Chern-Simons theory, we remember that in three dimension, Chern-Simons three-dimensional Chern-Simons theory is that okay, we can just write it like this. Yeah, maybe just in components now. This trace. So this is the three-dimensional Chern-Simons action, and its equation of motion would be quite similar to this one. So we will have this, and this should be 0. So this is the equation of motion for the Chern-Simons theory, and it looks quite like this Lacroix connection. But okay, so but here the M is in 3 dimensions. So in 3 dimensions, so we can, let's say that let's call this 3 dimension as something like that. And then if we fix that 3rd dimension, like the actual axis, sorry, this, and then we can also write that this, then we can say that this will depend on just this, and then this equation looks more like the Lacroix connection. But we are still missing the most important point in the Lacroix connection. The ATX does not depend on this spectral parameter. Spectral parameter is missing. So, so this is how this 4-dimensional Chern-Simons action was introduced. So now the 4-dimensional Chern-Simons theory. So the idea is that now we take the manifold to be, so this is the 2-dimensional manifold on CP1. So this depends on zeta and zeta bar. So zeta bar is the complex conjugate of zeta. And the gauge field of this theory is A, T, A, X, and then A, zeta bar. So we have 3 components. But there's no A zeta, no A zeta. Okay, so the 4-dimensional action would be constructed as this. Okay, so this is on a 4-dimensional manifold. So we need now this W. This is let's first say. Okay, this is one form, meromorphic one form, and we multiply it with this with the 3-dimensional Chern-Simons action actually. So this.
So there should be probably a wedge between the 1 form and the 3 form, right? Not times.
Sorry, what?
Yes.
Yeah,
Often we don't write the wedges.
Okay.
It's the implicitly.
Okay, yeah, sure. I mean,
Yeah, sure.
Yeah, if you want to write the Lagrangian in terms of the wedged products, then probably we should write it as, sorry. So, but this phi z is not filled. It's like initial data of this setup is not filled. Okay, so and then okay, so and now I should, let's see. Okay, so the equation of motion of this
Yeah, sorry, can I interrupt you? Just maybe I would suggest people to turn off their camera because we have some lag sometimes, so maybe that would help. I guess with the connection, because it's nice that everyone has the camera on, but I guess it might be better for the connection to turn it off. So we'll see if it, yeah, because like once every 2 minutes we have like a few seconds where we can't hear you, and then everything is really fast.
Okay, so let me just turn off my maybe.
Yeah, I don't exactly know how it works, but I think it might be better. So we'll see.
Maybe my upload speed is not very great, so maybe that.
Yeah, we'll see how it works.
Okay, sorry.
No problem.
Okay. I lost my screen. Okay. So new. Okay. So here the mu nu is now in 3 dimension. Yeah. And the general idea is that now we want to make some gauge transformation from this gauge field A to L such that
Can I ask? How is this the equation of motion if phi is not a field? Or how did you get this equation of motion?
This equation of motion is for the 3-dimensional part, I think. Well, no. Because phi does not depend on A, so it does not get into this equation of motion part. Well, we will see it clearly when we just go with.
So is phi a background, or are we going to integrate over phi in the path integral?
Yeah, we will. In the end, we will integrate our zeta.
Yeah, of course. But what about phi?
Well, phi is that we will choose the different forms of phi.
So it's a background field?
It's not field. It's just I don't know what. It's just some fixed data, I would say. So, and depending on what phi we choose, we can obtain different 2-dimensional theories. So here I just wanted to make the point what we are going to do. So, so we want our point is that we need to do some gauge transformation so that the third dimension zeta bar, it's the lambda is 0. So that means do this. This is 0. That means that since zeta bar is the complex conjugate of zeta, we can say that LTX depends on zeta meromorphically. So that is the main setup actually. And then now we would just.
What does this mean? A gauge L such that
we will do some parametrizations for the A, such that the gauge transformation, so that this lambda in this A zeta bar, here just some gauge transformation, and this will disappear.
What is L?
Well, L will be defined later as a Lax connection.
Oh, so you take A, you make a gauge transformation, and then you call it L. Oh.
So we will take this gauge transformation so that this part goes away. Okay, so now we can just, this was just the general point how we will go. So now maybe more in details. So, okay, so A is now one form. Zeta bar, D zeta bar, and there is no A zeta. Okay, so Chern-Simons section, the three-dimensional Chern-Simons form is that it's like this, delta A plus 2/3. So in components, we can write the action, four-dimensional action as this. Okay, now this sigma is two-dimensional thing, depending on t and x, and this, and then now we have CP1, dz bar, fz, and this Chern-Simons part. Let's write that's mu rho trace a mu, the mu a rho comes 2, 3 a mu a rho. Okay, like this, and this mu rho is in 3 dimension. So yeah. Okay, now we need to remember a little bit the 3-dimensional Chern-Simons theory, because we will use a lot this 3-dimensional Chern-Simons. So to write down this equation of motion for we varied the gauge field R, and then we calculate the Chern-Simons 3 form, right? So that means Chern-Simons 3 form in 3 dimensions is that okay, just write it. The Chern-Simons 3 form is this A delta A delta A dA plus 2, 3, and yes. So that is, so let's say trace delta A dA plus A delta dA plus 2A this, and then if you take B from A delta A, then this is delta A. So from here, we can write down this variation of Chern-Simons tree form. That's just trace to trace the A delta A. Sorry. FA delta A minus D trace A delta A. So this curvature term is just this, right? So we have this, and now we can just put this result into the four-dimensional case now. So we want to write down delta from omega wedged with Chern-Simons A. So this is just omega to trace FA delta A, and then omega B trace A wedged delta A. Okay, so which can be written as this. The first term is just as it is, omega FA wedged delta A, and then we need to write down the total derivative on this part. So that means we can write it as this trace A delta A plus D, the total derivative trace A, blah, blah. So this as a boundary condition, we can set it to be 0. Yeah. So, and now the variation of action would be just this trace omega. Also, we have this 2 here, so 2p, and then FA delta A minus I over 4 pi, and then the omega trace A delta A. Okay, so now okay, so this is the back term, and from here we will read the equation of motion. This one is actually called this two-dimensional defect term. We will talk about this later. Just a quick note here. Omega is that f z the z. So that means that v omega is that we cannot, we can only take dz bar. We can do only this, so that means we need to take f, we need to do something like this. So this is, generally it's just the distribution on CP1 with some support. With some support, we will call it zeta. That's actually the zeros of, no, it's a pulse of omega actually. So it's a distribution, so it is proportional to delta delta term. This is like this, so it's the standard thing, and this y is belongs to the support. So this two-dimensional defect term is on sigma times cross zeta. So this is sigma is that two-dimensional part and zeta is that pulse of this omega. And from the bulk term, we read of the equation of motion. That is just omega, which f a is 0. So, yeah. Then we can talk a little bit about the gauge transformations. So, gauge transformations. So there's something called formal gauge transformation. Formal gauge transformation. So this Chern-Simons theory is invariant under this gauge U. Let's call it. This is a real algebra valued, complexified real algebra valued transformation U, and such that the gauge field transforms as this U A this and then this and this. So it's a very general thing. So that means the curvature term is invariant. Yeah, well, it transforms like this and this, but omega, yeah, equation of motion is invariant under this transformation. So, and now we should start talking about this particular parametrization of this gauge field. So, suppose there exists the formal gauge transformation. Let's say something like that. It's a formal gauge transformation. So it's like this, such that this G this transformation of this gauge field on zeta bar direction is actually 0. So that means that it's equivalent to writing a z bar z bar like this. So it's the same thing as this, because if you put this transformation here, and you will just see that is this, and then this bar is
yeah, you're just mentioning the form of pure gauge, right?
yeah, it's pure gauges. So it will be just 0. So yeah. So I don't have to write it. So yeah. And now we can define also. Now we can also define L, which will be the Lux connection letter on part. This. So define this, and then and we can just write it let's just write it again. This, and then x is x, okay. This. So this is our parameterization of the gauge field. In terms of the G hat and L. Yes, L. So the G hat will be letter the only gauge field of this theory, and L would be the Lux connection. So okay. So
maybe I missed this. Is there any reason why we put hats on G? Is it, what's the difference between G and G hat?
Well, there is a G hat is like kind of general, and then we can call letter G particular case one.
I see.
So it's just naming. And so let's say now we got rid of this zeta bar direction. So now we should talk about this something called disorder defect. Disorder defect. Okay, so this L is actually but it can be holomorphic. Well, I mean, it cannot be holomorphic. If it was holomorphic, on CP1, then this LZ would be, it can be set as a constant because the dependence on zeta is like arbitrary, so it can be just set as a constant, but we don't want that. So let's say that LZ is meromorphic with some pole. And so the bulk term was that this, right? This, and with the H transformation, that is, it's still the same. So we can write this as omega. Okay. We can write this in terms of L. So we can write this. Okay. So we can write this. This, and also it's true is that zero, so that's why we called it the meromorphic, this L. So from this relation, we can write it like this. Okay, so we know that this distribution just looks like this. That means for lambda m to be lambda mu to have simple poles, simple poles like this, to have simple poles, omega has to have simple zeros. So this omega has zeros at y. This is, let's call it this. So this is called disorder defects. So omega has some zeros, and there is also something called order defect, and that's when omega does not have zeros. Does not have. So we will not talk about this. Just disorder defects where the omegas are in a rational form. So okay. Now we have mentioned. Okay, let's now go to. Okay, so but just so then now this L, this meromorphic L, you can write it like this. The constant part. And these are just one forms on two-dimensional manifold. Okay. And then if you want that integrable field theory to be relativistic, you would need that Ly to be either along the light cone directions, this or this. So you need to split that zeros, the disorder defects, kind of. So then you can write this, this. zeros on which is called this plus x plus and zeros along the x minus direction. So this happens. Okay. So this u and phi are the G complexified algebra valued fields on sigma. So now we can discuss about this G hat thing a little bit. So we had this parametrization. We had this parametrization here. So if you look at it, and you will see that this AZ bar is invariant under the if you just write it like this, and there is some phi, which is the smooth function transformation that is independent of zeta. Okay. So AZ bar is invariant under this, but so let me just write it up here. This Ln needs to be transformed like this. Like this. So this is the gauge transformation of the Lux. And then there's some, well, this four-dimensional Chern-Simons theory is also invariant under the general, the formal gauge transformation. It's also the gauge transformation is that this with u transform from four-dimensional n to this. So that means that it's equivalent to transform G hat in terms of this. You can just write some u in there. And here this transform, it's invariant. Okay. But this u should be compatible with the boundary conditions. Okay. So now we should say something about, let's say, well, then generally you can just call, make the u to be 1 over z bar, and then you know that you can just get rid of all the gauge degrees of all the degrees of freedom. Well, except for the boundary, the boundary terms. But probably we should talk about this after do the boundary, the pulse defect. Okay. let's just remember it's there. I'll just, well, let's just leave it here for the moment and talk about the false defect. So first we mentioned about this disordered defect that depends on the zeros of omega. Now we will talk about this false defect that depends on pulse. So generally, zeta is the pulse of omega. So, and then in the most general form, this pulse can be written as this does not have to be simple pulse, so it's just and then maybe also pulse. It's the most general form to write omega with pulse. So, okay. And then the defect term will come from this. You remember the defect term was written like this. Trace A delta A, and so this the omega is the distribution. So AC bar, AC. Okay, so if you have simple pulse, like now, if you have just simple pulse, then we can write this omega just like this. dz, and then this distribution will look like this. So just 2i pi maybe some L over 0, and this is it zeta r dz bar. So the distribution term, let's call it this. On R, zeta R is that just this on sigma trace A delta A on zeta R. So it's just, or in terms of the components, just we can just write it like this. New trace A new delta A on zeta n. So, well, if you have higher order pulse, then maybe let's just write it like this. This, and then yeah, there's this relation on higher order pulse that if you have this, then you can just have this relation. So delta z, this, and then z is r. So use this letter, and then defect term is just defect term on this r, zeta r will be L P bar, then the next, and then the z p trace a mu delta a mu at zeta r. So we need to take derivative of this trace. And the condition is that we want defect term to be 0. So that you need to put some conditions, boundary conditions on A. So that the defect terms, the sum of the defect terms are 0. So, so in this particular case, this dr, you can further write it as dl0 and mu trace a mu delta a mu, and then again. So maybe this comes with 0. Okay. And then the next order is plus mu trace. Now we need to take the derivative delta z a mu delta a mu plus mu delta z delta a mu at zeta r. At zeta r. So the boundary condition on A. So the choice is that it's the boundary, it's the pole. This A mu is 0. So also the delta A mu is also 0. So that the dr, these defect terms will be 0. Independently, these two terms will be 0 on its own. So, okay, so also this condition needs to be compatible. This gauge transformation should be compatible with this. So let's say this u, we wrote it as this, which is this, so this mu is that mu u, and then this was this word. So this needs to be compatible with the boundary condition. So then we wrote this as this. So that means from the transformation, its boundary should be this. And this. So that means that u is actually the boundary is independent of t and x. So it's just some. And you can write it as just let it be identity. So now we have this the disorder defect, and then we have false defect. And we also extracted the gauge fields. Fields. Oh, we did not extract the okay, so we briefly mentioned that this gauge fields G hat is actually the only gauge degrees of freedom, because we could, we have this freedom to write this, and if we write U to be G hat, then we can just get rid of all the degrees of freedom everywhere except the poles, because we just choose that at the pole we just chose that U to be constant. So the only remaining gauge fields are at the poles actually. So we have G, these are the degrees of freedom only on this, on the poles. So the physical degrees of freedoms are located at the boundaries. And now we can probably go to the PCR.
But I guess that's a sufficient condition for you. I mean, it's not necessary.
You mean
that U is identity?
Yeah, I mean, I guess it's the strongest.
It's stronger than what is needed.
Stronger than the constant, I guess. Yes.
Yeah.
Yeah, but anyways, even if it's not identity, and the degrees of freedom is still in the boundary conditions, and it's the boundaries. Because we cannot impose this. So if it's constant, then yeah, it's on the boundaries. So this is the general setup. Now we can maybe go to the examples. Okay, now PCM model. It's like what's the name? Chiral.
Principal chiral model.
Yeah, principal. Chiral model. So I think it's the simplest possible model. So in this case, we can choose omega to be this. So the Sylvain said that, okay, we can either just guess different omegas and get to the PCM, or just, since they already know how this this F set, this part looks like for PCM, because it corresponds to the twist function of this PCM model, and it has been calculated before, I think, based on the Hamiltonian approach. So they already know this twist function, so he can just, they just write this omega to be like this. So the point here is just to prove that this approach can produce PCM. So here the omega is like this. Then that means the pulse here, pulse of omega is either 0 or infinity. And this is a double pole, both of them. And then zeros of omega is either +1 or -1. Oh, also, there's reality conditions that one needs to put, namely, like this, so that if you put this and then in the end, your action will be real, I think. So this is the reality condition. So now, now we need to use the zeros and poles of this omega to produce two-dimensional integrable field theory. Yeah, so we also have these boundary conditions here. It's the poles, it disappears. And then this compatible gauge transformation with the boundary condition is that is that identity. Okay, so this G bar two-dimensional field is that this parametrizes that dz bar G hat -1. So this. So now, so we have this compatible gauge transformation, and this only physical degrees of freedom, as we said earlier, they are located at the boundaries. So this is at G hat this and G hat 0. There are the physical degrees of freedom, but there is also another gauge freedom that we mentioned before, like this. And this omega was independent of zetas. So if you apply this freedom again, and then we can fix the G at, let's say, G at Z 0 to be identity, at the infinity to be identity, then we have left only one gauge freedom, gauge degrees of freedom, which is now we will just call it G, just at the 0. So this is the only degrees of freedom on this two-dimensional functional field.
Right, that answers my previous question. So the head is, of course, for the 4-dimensional, and G is then down to the 2-dimensional.
Yeah, because
or maybe 3.
Yeah, G bar, yes. Yeah, I think so. Okay. So, and then from the disordered defects, we wrote down the Lacroix connections as this. This plus E plus X minus, okay. So this was the Lacroix connection. And for the PCM, the zeros of omegas are plus minus 1. Plus minus 1. So this Lacroix would be just, if you put plus minus 1, then you will have minus plus 1 plus phi plus minus. And this U and phi does not contain degrees of freedom because they will be G hat. So right, this. Like this. And then we also have this boundary conditions. Boundary conditions on A plus minus. So boundary condition would be as 0, and then so, and here that's the G hat infinities identity. So we impose this boundary condition, then that will produce us L plus minus at infinity to be equal to phi plus minus, which is 0. And now another boundary condition, plus minus at 0 to be also 0 at G0 is just G. So we apply this here, and A plus minus at G and the minus plus G U plus minus G minus 1. This and this. And this is 0. So that just tells us that the U plus minus is this. So finally, you can write this Lacroix as this zeta. So this is the lux. Now, okay, now we need to construct the action. So to do that, action. So from the three-dimensional Chern-Simons, the Chern-Simons term with gauge transformation, one can actually write it like this. Plus this, and Chern-Simons depending on L is that DL plus 2 or 3 of this, but L is actually along only dt and dx. So we cannot produce 3 widget products here. So this part will be just 0. And that means that okay, so that means the action, 4-dimensional action is just this. Choice L plus P omega choice this. So okay. So this delta V was distribution, so we wrote it many times. Okay. So it's distribution, and in our case, phi is a double pole. So this distribution will be written as a double pole. This set. And then like this, and use a bar. So since the G hat this identity at infinity, so the distribution from infinity will disappear. So we will have left only distribution from the 0. So there is no where there is no distribution at infinity, but there is a distribution at 0. So we will just write this 0. Now the first part, this defect part, will be written as just this part is that so this is easy bar trace and this thing L at 0. So so and so then trace G minus 1 and dg delta ZL at 0. So, and we just remember that plus minus G zeta. So we apply here, and then we will get now we go to the light one coordinates. So to the G here, the plus part, and then minus G part. So so the action is just reduced to this form. I mean, but there should be some so let's just color some coefficients there. So this is the actually action for the PCM, and this part in our case just goes to 0 because this is proportional to the residuals at 0. So this is actually 0, so it will disappear. But for other models, it does not have to disappear, and it's proportional to the this Witten term.
Yeah, that constant you wrote before in omega, and then you just forgot about it, I think. That K. Yeah, that should have been everywhere.
Okay.
It's the one form omega is proportional to the constant times z squared.
Okay, so yeah. You mean here also?
Yeah.
At the level.
Yeah, exactly.
Okay, so this is the history for PCM. So this approach produces correctly all those action and flux connection for this PCM. And now if you want to produce more complicated models like Young-Baxter's, then you take the omega to be, let me just check the omega for Young-Baxter. By the way, this PCM with Western atoms with non-one-nation residue. So here, if you take this and zeta minus delta dz, so this will produce you this non-one-nation residue at 0. So it's just this 0 is shifted to zeta 1. So this term does not vanish. So this will produce PCM width WZW. And then if you want to check the Young-Baxter, then for the Young-Baxter, the omega is a little more complicated, which is, let me just check. Omega Young-Baxter is that is and zeta squared, zeta squared and squared delta z. So you still have the zeros of omega is 1 plus and minus 1, but now you have the poles at infinity. So but the general approach would be the same, and then you also produce the correct lax and equation of motion and action from this approach. So this is all from me, and if you want to add more or comment, please go ahead.
Okay, thank you very much for the talk. So if anyone has any questions or comments, please feel free to unmute yourself. I guess we can also turn on the cameras. I don't know if it helped much, but yeah, I think maybe the lag wasn't that bad.
So I guess Ari more or less got to connected to what you were talking about, Stanislav.
Yes.
Yes.
The lex connections and the actions we saw was the things that I was deriving 2 weeks ago or 3 weeks ago. How long was it? Yeah, and this is like a different way to see the deformation, right? Because what I was doing is that I started with the principal Cair model, and then I just multiplied it with something or deformed it with something, and then looked at what equations must be satisfied for the thing I was deforming it, so I still get a flat and conserved current. But here it is from a different perspective, that instead of deforming something, you just choose a different, this one form, which looks very similar. The Young-Baxter and principal Cairo ones look similar, but they result in a different deformed model on this 2D after this reduction. Yeah. So it's like a different way of going to.
Actually, it's like more like going from the other direction. When you do the integrable field theory, so you just take some variable by constructing this Lacroix approach, and this is apparently hard to do it, I guess.
Sorry, can you repeat the last thing you said?
When you do this, when you take some integrable field theories, some field theories, and check that if it's integrable, then you need to construct this Lax and Hamiltonian approach, and this is probably difficult, more complicated, I guess. It's not always easier to find this Lax connection, I think. But here it's just quite simple approach. I think it's just systematic approach. You just construct this four-dimensional Chern-Simons theory, and then you choose different omegas and different boundary conditions, so that in the end you will receive this field theory that by construction you already constructed this Lax connection, so you don't have to check if it's integrable or not, because it's just integrable from the start. I think.
That's true. Yeah, but I guess the disadvantage of this approach would be that you also have to know something about the model to choose the omega and boundary conditions correctly to get something.
Yeah, well, I guess
Because,
maybe you can just play around with the omegas, just guess different forms of omega and then see what it would produce, right?
yeah. You might also get some trivial models, I guess, if you don't have enough poles or zeros.
And Sylvain said that you can always get almost all those two-dimensional field theories, you know, the already known and the new ones, but there are some theories like affine Toda model or Sine-Gordon. They are not derived from this approach, but probably it's just a matter of yes, the omega. Maybe it's more complicated for these cases.
So he said that you can't get the affine Godin model from this, or that he just doesn't know the correct omega for it.
When he said that it does not, this systematic approach does not contain affine Toda model.
Okay.
And Sine-Gordon model. But he did not say that it cannot produce those models, just, you know, for the moment, because this approach is like just 2 years old, so, you know, you need some time to.
Yeah, definitely. Yeah, I think he gives some comments about affine Godin models in the end of the lecture notes.
Was that about that twist function? About the twist function?
Yeah, also, I think.
Yeah. Because from the Hamiltonian approach, you can also calculate this phi function. I think that's called just twist function, and then that makes things more easier, I guess, to guess this omega.
Yeah, definitely. And that's for just for the principal Chiral model, or you can do it with the other models as well. Do you know if it is just for this one, or you can do it with all the models that you know?
I'm not sure. You mean this Hamiltonian approach?
Yeah. The calculating the twist function.
I think it was more general. Not, it said that for the PCM, that there was this paper by, let's see, I think Vicedo. So he calculated these twist functions. And the paper called four-dimensional Chern-Simons theory and affine Gaudian models.
Okay, do we have any other questions or comments? Okay, if not, then I guess we can thank Ari. Thank you very much for the nice talk.
Thanks.
And yeah, please let us know if you have any wishes to give some talks, like or any of you, and then I guess we will discuss with Patrick the future of this, like if we're gonna be maybe doing once every 2 weeks, if we don't have enough speakers, or if we do have enough speakers, we'll continue doing every week. So we'll let you know. And okay, thank you again, Ari, for giving the talk, and thanks everyone for coming today.
Thanks.
Bye.
Bye.
Bye.